I hope you guys had a productive weekend, break. Did something, one thing? No. Did anyone work on their homework? Okay. One hand goes up. Is that because the rest of you are just too shy to raise your hand? Yeah, that's what I'm gonna tell myself when I go to sleep tonight. All right, so let's take a look at what we're doing. We are covering, today we're looking at inverse functions and exponentials. We're in the final stretch. We've got like 5 or 6 weeks left and we're done. Don't quit now. If you took the week off, don't get stuck in break mode. 4.1 is on inverse functions. So one thing we need to know for this is the idea of a one-to-one function. One-to-one function. For each x value, there is one y value. There is only one y value. That's actually something you already know. I just put into words, this is the vertical line test. The vertical line test is when we draw the line, the thing over the graph, every time we never cross the graph more than once. So there's only one y value for each x value. The other part of a one-to-one is for each y value, there is only one x value. Guess what this test is called? It's the horizontal line test. Yeah. So when we go to draw a line, pick a line horizontally down the graph and move this, we never cross the graph more than once horizontally either. So we want to be able to do it both ways and cross the graph only once. So some examples of functions that are one-to-one. F of x equals mx plus b. As long as m does not equal 0. That is a line. Could be like that, could be, going downward. What about something like this? What does this do? So I can see no matter what x value I plug in, I get a y value that's kind of unique to it. But what about the other way? Like this is like saying y equals the square root of 49 minus x squared. Is there different values of X that I could plug in that are gonna give me the same Y? What's X squared do? What happens if I stick in 1 for X? What happens if I stick in -1? 49 minus 1 squared is the square root of 48. And square root of 49 minus -1 squared is also square root of 48. This is not 1-to-1. If you're not sure how to go about graphing that, I think putting in the Y helps, because then I could square both sides. And I get Y squared equals 49 minus X squared. Note that Y was always greater than 0 in the original. And so that has to stay true. If I add X squared to both sides, what do I get? What is this an equation of? Haven't we done this? It's a circle. This is a circle with radius r equals square root of 49, which is 7. But since y can only be the positive part, it's just a half circle. So this equation is the whole circle. Y equals square root of 49 minus x squared is the top half of the circle. So sometimes you can do little things to see what it looks like graphically without having to pull up Desmos or some graphing utility. And I can see right there, this does not pass the 1-to-1 test. It passes the vertical line test just fine. But it does not pass the horizontal line test. It's crossing the graph twice there. So I'll write that down. Passes vertical, but not horizontal. And that's called the horizontal line test, or part of what we did. Everybody ready? So does that function pass the vertical test? Yeah, I saw it had 9, yes. Does it pass the horizontal test? No. So in this case, f of x is a function, but it is not a 1-to-1 function. What about Does that pass the vertical test? Can I take something, the line is vertical and cross the line more than once? No, it doesn't do that, does it? So it doesn't cross the line more than once, so it passes. If I do it horizontal, does it cross the line more than once at the same time? No, it doesn't there either. So it passes the horizontal line test. This one is also 1-to-1. This one is 1-to-1. I already said something like mx plus b. That passes it. It's 1-to-1. Something that's good to note, a function that's either always increasing or always decreasing. Is 1-to-1. What about, and we just got done doing this one in the last chapter, the rational function 1/x. You have asymptotes for both of the axes. Does that pass the 1-to-1 test? What?
No.
Why?
It's not crossing anything. It's not crossing the edge or something, it's just going like random.
Like along one of the axes? That's not a problem. So long as we do the vertical line test and the horizontal line test and we never cross the graph more than once, we pass the 1-to-1 test. So I come along, I'm doing the vertical line test. I hit the graph only once, I hit the graph only once, I'm still hitting the graph. Right in the middle, I'm not hitting the graph at all, but again, that's not a problem, as long as it's not more than one. And then I start hitting the graph again, but it's only once. So it's passing the vertical line test. If I do the same thing with the horizontal line test, I'm hitting the graph just once. I get to the x-axis, I'm not hitting it. As soon as I go above it, I'm again hitting it only once. Y = 1/x is a 1-to-1 graph. So if a function is 1-to-1, there is an inverse function for it. If our first function is f of x, the inverse has the notation f negative 1x. There's a handy way to test if two of them are function, or two things are inverse functions. An easy way to test two functions are inverses of each other. F of g of x, or fog x, has to equal x. And g of f of x has to equal x. And remember, this thing on the left, fog x, is really, we're taking g of x and we're putting it inside of f of x. And for the g of f of x, we're taking g and we're putting f of x inside of it. Example. We want to know, are these inverses? So I can take g of x and put it inside of f of x. F of g of x is f of 1/2 x minus 5, which equals, I've got 2 times 1/2 x minus 5. If I multiply this out, I've got 2 times 1/2 x is x. 2 times -5 is -10 plus 5. And I get f of g of x is x minus 5. Which does not equal just x. So these are not inverses. What if I change g of x? What if I make g of x let's do 1/2 parentheses x minus 5 that way. And we'll keep f of x the same. F of g of x here, now I'm plugging in 1/2 x minus 5. Into 2x plus 5. the 2 and the 1/2 cancel, and I'm left with x minus 5 plus 5 equals x. I then want to check the other way, but usually when one of them works, it's a good sign the other one's gonna work. Let's try plugging in f, which is 2x plus 5, into g. Plug in 2x plus 5. The 5 and the negative 5 cancel each other. I have 1/2 times 2 times x is also just x. This means these two are inverses. They are inverses. And it means I can say g of x is really f inverse x like that. Check this out. I do a little x and y table, and I stick in -2, -1, 0, 1, and 2. This one is 5, 7, 9, 3, and 1. When I do f inverse of x, which we just showed was 1/2 times x minus 5. I'm going to change it up. I'm going to plug in 1, 3, 5, 7, and 9. You will see that when you do this, like if I stick in the 5, I get 0. If I stick in 7, I got 7 minus 5 is 2. And 2 times 1/2 is 1. If I stick in 9, 9 minus 5 is 4. 4 times 1/2 is 2. If I go the other direction, I'm going to get those values. That's kind of pretty fucking neat. The domain of f of x is the range of f inverse. And the range of f of x is the domain of f inverse. Let's scrap these two lines in decimals. What happens when I stick in X? The line Y equals X. This red line was my f of X. The blue line was my f inverse of X. And if I center it a little bit better, it might be easier to see. The blue line is just a reflection of the red line across that axis. The graph of each one of these is the reflection of the other across y equals x line. The simplest way to put what we had up here in words. If f of A equals B, then f inverse of B equals A. If you graph one, all you've got to do to graph the other is swap X and Y values. Again, this requires these both need to be, F needs to be 1-to-1. Otherwise, we won't have an F inverse. I think we could find it, but it's not going to be a function. You could find an equation for it, but it's not a function. And we want it to be a function. So if they give you some points. Set of points, -2, 5. -1, 2. 0, 1. 1, 2. And 2, 5. I gotta go through to find out if I can find an inverse. Neither X nor Y repeats. In this set, we have some repetitions though, right? When X equals 2 or -2, Y equals 5. So Y repeats. So this is not 1 to 1, and we can't find inverses. This set, on the other hand, does. Hell happens. This fucking son of a bitch. I have my X values are -2, -1, 0, 1, and 2. They don't repeat. My Y values are -8, -1, 0, 1, 8. They don't repeat. So this function has an inverse. This is actually Y equals X cubed. The inverse function have points -8, -2, -1, -1, 0, 0, 1, 1, and 8, 2. So I know the equation of this function, the one I drew here. How can I find, let's say this is f of x. How can I find f inverse? Or an equation that models it? I am so happy you asked. That was so clever of you guys to ask that question. To find, if you know, if f of x is 1 to 1, we can find f inverse of x by doing these steps. A, replace f of x with y. So we're going to write it, we're not going to have the f in there, we're just going to have the y in there. I mean, it's doable with the f of x, but it's fucking tedious as all hell. It gets really ugly having it in there. Then the magic operation there here, I actually mentioned it just a second ago. all you have to do is swap X and Y. That's what we're gonna do. Swap X and Y. Then solve for the new Y. Finally, replace Y with F inverse of X. I'm gonna do that up here. I said f of x equals x cubed. And I'm gonna make that y. So I have y equals x cubed. That's step A. Step B. Everywhere I see a y, I'm gonna put an x. And everywhere I see an x, I'm gonna put a y. And now I want to solve for y. How can I get y by itself here? Take the cube root, yeah. So take cube root. I'm gonna get y equals the cube root of x. Finally, I'm gonna replace y with f inverse. Notice if I do f of g of x, if I take, this is my g. If I take the cube root of x and stick it into x cubed, I just get out x. And if I take f and stick it into the other one, I have the cube root of x cubed. That's also just x. Do a couple examples. Ones that are a little bit quicker. Or aren't too bad. Let's say I have g of x equals 4x minus 7. And I want to find the inverse. What is g inverse of x? Well, we already know this is a line, y equals mx plus b, so it does have an inverse, it's 1 to 1. So I can do it. This is 1 to 1. So I'm gonna replace g of x with y. And then keeping everything else the same, I'm going to swap the positions of x and y. Y becomes an x and x becomes a y. Finally, I solve for y. I can do this by adding 7 to both sides. And then dividing by 4. And I get y equals 1/4 x plus 7/4. And finally, I'm going to replace y with g inverse. Let me give you guys one to try. So if the h of x is 1 to 1, find h inverse. Is it 1 to 1? Do we meet that requirement? We've already shown how to graph things like this. X cubed, we already said was 1 to 1. What happens when I add 5 to x cubed? What happens to the graph of x cubed? It just goes up 5, right? So all the points have moved up. The picture of the graph, though, has not changed. Which means anything that was passing vertical and horizontal is still passing vertical and horizontal. This does pass the 1 to 1 test. So how do we find an inverse? So we're gonna put in a Y. We're gonna swap them some bitches. And now we solve for Y. Raise each thing to the 1/3 is the same thing as taking the cube root. We get Y equals the cube root of X minus 5. Which makes that H inverse. What about f of X equals the absolute value of X? First off is F 1 to 1. What's the graph of the absolute value of X look like? Looks like a V, yeah. So f of X is not 1 to 1. There is no F inverse. Doesn't exist, or you could write DNE. Like it shows up on a test. All right, 2 more. Then we'll go on to 4.2. The reason why we're going to do 2 more is because these ones are the bitches. So rational functions can have inverses. Not all do. Oblique asymptotes rarely do. Ones with oblique asymptotes rarely do. I'm going to go so far as I think I could probably safely say never. But I don't want to say never just in case. No, I can't imagine a situation where not a single, I'm gonna say never. Also the ones where, like, they're both squared, there's a square on top and bottom, they tend to go the same direction. But this one does. So, finding the inverse. This could be a bitch, so what I'm gonna do is I'm gonna write everything down that is not an X or a Y before I start replacing them. Now the Y becomes an X and these become Ys. Let's clear fractions. Multiply both sides by Y minus 5. Remember, our goal after we switch the goal is to solve for Y. So having a Y in the denominator is never going to work. So we want to get rid of the fractions. What we do now is we distribute. And I have X times Y minus 5X equals negative 3Y plus 1. My terms with a Y in it are right there. I have an XY and I have a negative 3Y. I want to get those on the same side. So I can do this by adding 3Y to both sides. And while I'm doing that, I'm going to move the 5X to the right. How can I get my Y by itself here? I've got two things with a Y in it. Let's factor it out. Now, if I divide both sides by the thing multiplied by Y, I will have Y by itself. Divide both sides by X plus 3. And I get Y, which is really F inverse of X, equals 5X plus 1 over X plus 3. I'm a big fan of that type of problem on the test. Just telling you that now. I like that problem. It tests your factoring ability. It tests a bunch of stuff. You ready for one more time? We'll kind of skim through this because I want to get to the exponential. The hard part is only the hard part of this one is the beginning. Well, paying attention. X squared plus 4 by itself is not 1-to-1. It's a parabola. But if I restrict x to be less than or equal to 0, I just have that portion right there. And that portion is 1-to-1. But this is a domain restriction. If we go through and do the swapping of things, that would be what we would get if we solve for y. Which would be f inverse. What did we say the domain of f of x was in relation to f inverse? Do this in the very beginning. I had the two x and y charts. The domain of f of x is the range of f inverse. So if there's a restriction on the domain of f of x, there's a restriction on the range of f inverse. And all I'm doing is swapping the letter. So I don't want I can't do plus or minus, which means f inverse of x is only the negative square root 1. Because that forces that one's hand. The restrictions on the domain of f force restrictions on the range of f inverse. All right, you guys ready for some more fun stuff? I think 4.2 is a little bit easier. It's not too bad.
Wait, if we only do the negatives, wouldn't it go against the range restriction?
What?
If we do the negative instead of the positive, doesn't it go against the
Why
range
be less
restriction?
than 0? Less than 0 would make everything negative. Remember, it's y, not x.
Mhm.
So what I end up doing is, if I do the symmetry of this and reflect it across the graph, this is going like that.
Oh, okay. So I guess my question is, when we had the plus or minus square root x minus 4, why did we go with the negative? Oh wait, never mind. I see
Less
now.
than 0?
I get it.
Okay, good. No problem. I'm glad you asked. Let's take a look at 4.2. 4.2 is on the exponential functions. Functions of this form come in the form y equals a to the x power. Assuming a is greater than 0. And a does not equal 1, because a equaling 1 is boring. 1 to the x is just a bunch of ones, right? This actually has a few properties. Property 1, a to the x is a real number for all x. A to the b power equals a to the c power if and only if b equals c. If you go further in mathematics, they abbreviate this sentence here, or this part here, as IFF. It's a shorthand saying if and only if. For the first part to be true, the second part has to be true. And if the second part is true, the first part has to be true. This requirement actually makes it meet the rule that this is a one-to-one function. So exponential functions are one-to-one. Then they start breaking up A into two different groups. Let's look at A greater than 1, and let's look at 0 is less than A less than 1. Then we have if B is less than C, then A to the B is less than A to the C. This means the function is always increasing. And this one, we do if B is less than C. Then this switches. A to the B is greater than A to the C. And in this case, the function is decreasing. And we'll look at examples of both of these. You guys ready? Easy way to pick two number or pick A's that show both of those. We're gonna do on the first one, f of x equals 2 to the x. And we'll also look at f of x equals 1/2 x. This can get pretty unmanageable to graph pretty fucking quickly. So we're only gonna do 3 points on each. We're gonna do -1, 0, and 1. If I stick in -1 right here, I've got 2 to the -1, which is when we have a negative exponent, what does that mean we do? Anybody? Not quite. I is when we did complex numbers. Negative exponents, flip it over. What's the number to the 0 power? 1. And if I have 2 to the first, that's just 2. We see if I stick in -1, I've got 1/2 to the -1. And if the -1 makes it so I can flip the fraction over. If it was anything but a 1, we'd have to do the power as well, but 1 just flips it. That makes it 2/1, which is just 2. 1/2 to the 0 is just 1. And 1/2 to the 1 is 1/2. I'm gonna draw my same graph. So 2 to the x will be in red. We've got -1, 1/2, 0, 1, and 1, 2. There's another neat caveat of f of x. Maybe I should have mentioned exponential. I should have mentioned it earlier. If f of x equals a to the x, and a is greater than 0, f of x is always greater than 0. Never even equals 0. Which means the x-axis acts like an asymptote. So this goes like this, and this goes like this. That's 2 to the x. And if I do the other one, we'll do this one in green. I've got -1, 2, 0, 1 again, and 1, 1/2. Here's another way to write this 1/2 to the x. This, what happens when I flip a fraction over? We just did it here. We make the exponent the opposite sign. This is the same thing as 2/1 to the negative x, or 2 to the negative x. So that will be a general rule, general thing that we're going to follow. Assuming the base is always greater than 1, it's always going to look like this. It's going to be low, close to 0 on the left, and it's going to go up, unless you've got some sort of shift by adding something to it. Like if I added 2x or added a 1 to it, it's going to push all the values up by 1. But it's still going to do this asymptote thing like this, and it's still always increasing. We have a value between 0 and 1, like here, or if the exponent is a negative, like that, it's going to be decreasing. This happens every time. And so for f of x equals a to the x, they say that this is the exponential function. F of x is the exponential function with base a. So exponential means my variable is the exponent.
Can you move the paper up a little?
Yes, the, if I were to do this in general, let's do it in general with a to the x. Let's do this graphing idea, because the pattern holds. Now a greater than 0. I could do a few more. If we do -2, -1, 0, 1, and 2. If a is small enough, you can get it on a normal graph. This is a to the -2 power, which is 1/a squared. This is 1/a. This is 1. This is a. And this is a squared. It's always going to have that graph that treats the x-axis as an asymptote as x goes to -infinity. It becomes an asymptote. It's always crossing at 1. And wherever this is 1, this value is a. Where we have -1, this is 1 over a. So the domain is all real numbers. The range, y has to be greater than 0. Not even equals 2. We never have an equals. And this function is increasing and continuous everywhere. When we switch this and we do a is between 0 and 1. The y's here just go upside down. 1 over a squared from the top one becomes a squared here. And as I keep going down the list, I divide by a. You really only kind of need to plot 3 points. Those. If you do the 0 and you do the -1 and the +1, that's really all you need. So -1 gives me an a. 0 always gives me a 1, and this one gives me a 1 over a. Same domain and range. The only change is this one is decreasing and continuous everywhere. So why don't you guys graph one of these? Why don't you guys try graphing f of x equals 3 to the x? What do you get for y when you have x equals -1, 0, and 1? One third, 1, and 3, yeah. What if we had f of x equals -3 to the x? Not in parentheses, just 3 to the x, then there's a negative in front of it. What does that do to the y values? It should be the same as 3 to the x. Like this, but then we multiply by a negative. So it should be -1/3, -1, and -3. So having it negative, all this did was flipped it over the asymptote. Remember when we were doing polynomials and we had stuff like x minus h to the n power plus k? What did the h do here? H moves the graph right. And k moves it up. Same thing applies for f of x equals a to the x minus h like that plus k. Same idea applies. So if I did f of x equals 3 to the x minus 2. It's going to be the same as 3 to the x, just shifted right twice. It's that line right there. All right. So those are exponential functions. How do we solve an exponential equation?
Can you put that last page back up for a little bit? I just need to, I can
Yeah.
screenshot it. Thank you so much. Okay, I'm good.
Can you mute yourself, Senzi?
Because then people will be getting the things. I want to do a Cambodia on a room trade. I guess I'm good.
Oh, there she goes. She goes. Okay, so until we have more tools in the toolbox, what we're gonna do is, the idea is get the bases to look the same. If you can do this, this is the easiest way to solve it. We will learn other ways to solve it later on. What do I mean by this? If I have 5 of the x equals 1 over 125. Can I write one over 125 as 5 to some power? I can. So the easiest way you might see about doing it is, first off, factor that 125. That's 5 and 25, and this is another 5 and 5. This is really 1 over 5 cubed. And if I move it to the numerator, I make the exponent negative. So right now I have 5 to the x equals 5 to the negative 3. And the rule we had, one of the first properties I told you was, if the bases match, the exponents must match. Which means x equals negative 3. That's not too bad, is it? You're gonna have to do some number manipulations and shit like that. What if I have 3 to the x plus 1 equals 9 to the x minus 3? I can make it 3 squared. So let's do that. I'm going to put in parentheses like that. Because that's what's really happened. What do we do to deal with this? You multiply. Excellent. This is 3 to the 2 times x minus 3. Or 3 to the x plus 1 equals 3 to 2x minus 6. The bases match, so the exponents match. This means x plus 1 has to equal 2x minus 6. And we could solve for x. So we're saying x equals 7. Is this true? Does this make sense? If I have 3 to the 7 plus 1, is that the same thing as 9 to the 7 minus 3? Well, this is 3 to the 8. And this is 3 squared to the 4. So yeah, that does work. So x equals 7 works. One of the more common uses in real life for non-engineering things for exponential functions is the compound interest formula. A equals P times 1 plus R over N to the NT. P is the principal deposit or starting deposit. R is the annual interest rate. N is the number of payments in a year. And T is the number of years. Ideally, if you have something that's you're getting compound interest, you want it to happen more frequently than less frequently. Like semi-annually is only twice a year. Monthly, you're getting 12 times they give you interest. And what it's doing is whenever they're giving you interest, they're taking whatever you have as the current balance and applying interest to that and giving interest on that. So if you start off with like $1,000 and you get like $100 interest the first time, you're now at 1,100 and they pay you interest on the 1,100, not just the 1,000. So you start gaining more interest on the interest you just earned. So ideally, this goes as fast as fucking possible. When you do it like daily would be 365 right here, which is pretty fast. Each little increase isn't a lot of interest, but since it's happening daily, you get a lot higher value than if you did it like once a month. Not a lot higher, but enough higher. And then when later on, we will learn about continuous interest, where it's just like seconds. Every second you're getting interest. And A is the final amount. I didn't say that. So let's say you deposit $2,500 into an account generating monthly interest. We want to find how much does the account have after 10 years? And how much interest did you make?
What is the rate?
If the rate is, let's say it's 3% annually. Right, we were gonna go through that and not have all the information we needed. So we can start plugging in what we know. The initial amount I deposited is 2,500, that's my peak. My rate is 3%, but we can't have the percent in there, which means we have to convert it to a decimal. R is 0.03. Monthly would give me 12 right there. And then I have n equals 12 times t equals 10. Let's get my calculator out. So this is 2,500 times 1.0025 to the 120. I recommend doing it in steps. This is really easy to fuck up. Now I'm going to take that and I'm going to raise it to the 120 power. If you write down every step that you're doing, like the set intermediate values, here's how it makes it easier to check your work afterwards. That's dollars. So that's how much I would have after 10 years if we didn't take any money out, we left it alone, and just kept generating interest, and it was only compounded monthly. I recommend playing around with it, see what happens if you change it daily, see what your amount would be. Just so you see just how much of an impact it has. And then how can I figure out how much interest I actually made? Like, what was my profit for doing this? What was it? It is. How did you get that? Right. A is really the principal plus the interest. Your total amount is the principal plus any money you made is interest. So interest is A minus P. So 33, 73, 38 minus 2,500 gives you 873.38. For I. That's it. That's all we got for today. Was that on everything you would hoped it would be? It's pretty exciting, right? This is my happy week. Yesterday was my anniversary and Thursday is my birthday. So that means I'm spending my birthday with you guys, because this is how much I care.
Bye, have a good day.
You too? Ah. I have to show up. I don't have that luxury. I could, but I'm not going to. We got shit to do. Yep. As much as I want to, and you know I want to.